Hi class, in this video I want to review the basics of two fundamental vector operations, the dot product and the cross product. Let's start with the dot product. If we have two vectors a and b, the dot or scalar product a dot b takes these two vectors and gives us a number. Geometrically, the dot product has the following interpretation. If this is the vector a and the vector b and theta is the angle between them, then a dot b is the product of the lengths of a and b, the magnitude of a times the magnitude of b, times the cosine of the angle included, cosine theta. From this geometrical interpretation, you can see that it doesn't matter whether we take a dot b or b dot a, we get the same dot product. In terms of components, this is very simply expressed as follows. If A is AXI plus AYJ plus AZK, that is, it has components AX, AY, and AZ with respect to a right-handed rectangular coordinate system with basis vectors I hat, J hat, and K hat, and B has the corresponding relationship with components BX, BY, and BZ, A dot B, which is a geometrical and coordinate-independent object, can be expressed in terms of the components algebraically as the product of the corresponding components summed together, AX, BX plus AY, BY plus AZ, BZ. Again, let me emphasize that the dot product actually doesn't depend on the coordinate system that you use it in. It can be computed algebraically in terms of the components in a particular coordinate system. So we'll often see physical laws expressed in terms of dot products because that's the physical law doesn't depend on what coordinate system we use. But when we go to calculate something, we'll often establish a coordinate system, compute the components, and then compute the dot product. From these definitions, we see that the x component, ax, is just a dot I hat. Ay is the vector a dotted into its j component, dotted into j hat. And similarly, the z component of vector is the vector dotted into k hat. Next, let's talk about the cross or the vector product. Unlike the case of the dot product, in this case, it takes two vectors and gives us another vector. C, the vector C, is the cross product of A cross B, and we write it this way. C is A cross B. Geometrically, it has the following interpretation. If we write the vector A as this one and the vector B as this one, again, theta is the angle between them, we form a direction perpendicular to both A and B, and given by the right-hand rule, we put our right hand in the direction, with our fingers pointing in the direction of A, we curl toward the direction of B, the direction of our thumb is the direction of C, and the magnitude of C is given by the product of the magnitudes of A and B, now times the sine of theta, the sine of the included angle. So if A and B are perpendicular, C has a magnitude equal to the product of the magnitudes of A and B. If A and B are actually in the same direction and theta is 0, the cross product vanishes. This has the interesting property that A cross B is minus B cross A, because if we do B cross A, the right-hand rule will go from B to A and will point down instead of up. So this is a skew-symmetric operation. It's not commutative. If we look at our basis vectors, I, J, and K for a orthogonal rectangular coordinate system, the Cartesian coordinate system, I hat cross J hat is K hat, J hat cross K hat is I hat, and K hat cross I hat is J hat. This system this actually defines what we mean by a right-handed coordinate system. If you want x, if x is in this direction, y is in this direction, positive z is in that direction. Again, we can reduce the geometrical object a cross b into an expression involving its components. If we use these basic cross products, then we can actually compute that a cross b is this combination AYBZ minus AZBY in the I direction. Note that it doesn't involve the x components of a or b. In the j direction, it's AZBX minus AXBZ, and in the k direction, it's AXBY minus AYBX. There's a simple mnemonic that you've probably learned before, and we can think of this cross product. We can compute it by computing the determinant of a matrix where we formally put the basis vectors, here I've written them as x hat, y hat, and z hat across the first row, and then the components of A, which is the first vector, in the second row, and the components of B in the third row. If we evaluate this by expanding in cofactors, for example, in the x direction, we get AYBZ minus BYAZ, which is exactly what we get here. We have to take into account that when we do the second cofactor, we need a minus sign, but the pattern repeats and gives us both the y and the z components of the cross product.